In the second part of mathematics for games, let's first look at transformation of coordinate spaces. So as we discussed previously, coordinate spaces map different coordinate systems. So you can easily convert vertex to a different space. So a transformation alters the size, orientation, shape, and objects that are copied from one coordinate space into another. There are two ways in which you can do the transformation. You have active and passive transformations. So in active transformation, it only changes the physical position of a point or rigid body, which can be defined in the absence of a coordinate system. In contrast, the passive transformation system only changes the coordinate space in which the object is described in, the object space that you use to describe the object. When we describe a coordinate space and when we describe the origin, we come across something called the world space or the global reference frame. So here the position of other coordinate spaces can be expressed in terms of the world space, and this space cannot be expressed in terms of any larger or outer space. Then when it comes to the object space, this is the space associated with each object that belongs to the world space. For example, when we take the camera space, the object space associated with the viewport used for rendering is called the camera space. Then when it comes to the upright space, it's a special space associated with each object. It's halfway between the world space and the object space, in the sense that the axes of the space are parallel to the ones of the world space, but the origin of the space is coincident with the origin of the object space. So why do we have the upright space? We have it because it makes our life easy when we want to transform a point from the object space to the world space. If we want to go from the object space to the world space, the transformation itself becomes easy because having this upright space divides this problem into two parts. The first part is you convert the object space into upright space. So here what you do is a rotation. And the second one, this is the first one. The second is what is in upright space now, you convert that into world space. This is simply a change of location. So this problem can be divided into two sub-problems since you have the upright space. Then let's go to basis vectors. So a set of vectors in a vector space is called a basis if every element of the vector space can be written in a unique way as a finite linear combinations of elements of the set of vectors. Say for example, you have a set of vectors, let's call this B, and if your vector space is V, you call the set of vectors basis if every element of V can be written in a unique way as a finite linear combination of elements of B. The coefficients of this linear combination are referred to as components or coordinates. That is what we usually use. So the coefficients are called coordinates of the vector with respect to B. The elements of a basis are called basis vectors. Now, if we look at vector basis, a vector basis of a vector space, so since our vector space is V, a vector basis of a vector space V is defined as a subset V1, V2 up until Vn of vectors in this vector space V that are linearly independent and span in the vector space V. So consequently, if this is a list of vectors in V, then these vectors form a vector basis. But to do so, each and every vector has to be an element of the vector space V. That is what a basis vector basically means. So a vector basis of this space V means that when you have this list of vectors in V that are linearly independent and they span V. So if this set of vectors is a list of vectors in V, space V, then those vectors form a vector basis if and only if every V is an element of the space V. Okay, now let's come to matrices. A matrix is a rectangular array of numbers arranged into columns. The horizontal and vertical lines of the entries in a matrix are called rows and columns. And the size of the matrix is defined by the number of rows in the columns that it contains. So we can perform certain operations on matrices. For example, we can add, subtract. Matrix addition is commutative and it is also associative. And then scalar multiplication is also possible. So the properties that are available in matrices, operations on matrices, is we have the identity property. identity, and then we have a distributivity. We have associativity. And then we have the null property, and what we call the additive inverse. This is called the additive inverse. Okay. Now, when it comes to matrix multiplication, earlier we spoke about scalar multiplication, which is simply multiplying a value through the elements of a matrix. But when it comes to matrix multiplication, it is multiplying every element of each row of the first matrix times every element of each column in the second matrix. Scalar multiplication is much more simple than matrix multiplication. When multiplying matrices, the elements of the rows in the first matrix are multiplied with the corresponding columns in the second matrix. So when we basically do matrix vector multiplication, we need to view the vector as a column matrix. We define the matrix vector product only when the number of columns in matrix A equals the number of rows in vector X. Okay, the number of columns in the matrix should be equal to the number of rows in the vector. So if we take an example here, we multiply this column with this row in the vector. Once again, this column will be multiplied with the same. So this is why we view the vector as a column matrix. And the multiplication is defined for the case when the number of columns in the matrix is equal to the number of rows in the vector. You can see it here as well. This is multiplied by this, and then this finally with this. Now we come to matrix multiplication. So here what we basically do is, in the matrix, you simply view the columns in the matrix just like how you looked at vectors in the previous matrix vector product. Since we look at vectors as column matrices, the matrix vector product is simply a special case of the matrix multiplication. So the multiplication between the matrices A and B is defined only if the number of columns in one matrix is equal to the number of rows in the other matrix. Okay, so this is a special case of matrix multiplication. Then when we look at transformation in matrices, the rows of a matrix can be interpreted as the basis vectors of a coordinate space, and to transform a vector from the original coordinate space to a new coordinate space, we multiply the vector by the matrix. So this transformation is defined by the basis vectors. The linear transformation preserves straight lines and parallel lines remain parallel. Okay, now let's look at transformations are transformations are functions that map vectors to other vectors. They can represent geometric operations which are caused by movement or action, as well as changes of coordinates which are caused by changes of interpretation. Many common spatial transformations, including translations, rotations, and scaling, are represented by matrix vector operations. Changes of coordinate frames are also matrix vector operations. As a result, transformation matrices are stored and operated ubiquitously. When we look at linear transformations, this is the type that we can represent as a matrix operation, basically saying y equals ax, where A could be an m by n matrix, x is an element of, and also y and x both. So in particular, in a 2D space, this operation takes the form after transformation. If you get this, so this is the answer that you will get in 2D space. Similarly, in 3D space, you could do the same thing, where you have a 3D coordinate as well as qz and pxyz, and you get a 3D answer in the 3D coordinate space. So when it comes to 2D rotations in the 2D space, rotations about the origin by an angle theta can be defined as a linear transformation. So let's consider two reference frames with a common origin O. The pre-rotation axis will be x and y. This is the pre-rotation axis, and the post-rotation axis are, so pre-rotation axis will be x and y, post rotation, after you rotate, what you get is x dash and y dash, as you can see here. So when we depict x dash on top of x and y, we shall see that x dash has coordinates, x dash will have coordinates cos theta, sin theta, as we can see here. It's a bit more involved, but not much, to determine that y dash has the coordinates negative sine theta, cos theta. Now, let's say that a point P was rotated to point P dash. Let's derive how to determine its new coordinates relative to the original reference frame. So if we say that P dash has the coordinates Px, Py relative to its post-rotation frame x dash, y dash. Since the distances do not shrink or grow when the objects are rotated. Okay. So specifically, P dash is obtained by walking Px units from the origin in the direction of x dash. And then you walk Py units in the direction of y dash. Then only you will be getting Px and Py as P dash's coordinates, right? Therefore, to determine the coordinates in the original reference frame, we can use the fact that the coordinates of x dash and y dash are known. So P dash is equal to Pz times x dash. So this is the original x coordinate of P. Py times y dash. X dash and y dash. What does this mean? Now we know what x dash and y dash are because here we have already given what it is. So this will be so when you rotate an angle, when you rotate at an angle theta about the origin to achieve a new point P dash, to calculate the coordinates of P dash, we first obtain the coordinates of the transformed axis x dash and y dash, and then we do a small calculation using the coordinates of x dash and y dash, and the units obtained by walking how many, the units that the units that you need to take from the origin in order to meet P dash in the direction of a particular axis, rotated axis. Okay, then when it comes to 3D rotations, before we go to 3D, there are certain properties that we need to talk about. The matrix composition theta 1 theta 2 equals r theta 1 plus theta 2. This gives the rotation matrix for the sum of the angles. And then we have a determinant. Due to the identities, cos minus theta is theta, and this, the rotation about a negative theta is also equivalent to the transpose of that matrix. The transpose is also equivalent to the matrix inverse. In other words, rotation matrices are orthogonal. And then vector norms are invariant under rotation. The rotation matrix is only dependent on the argument's value modulo 2 pi. These are only for additional knowledge, just to read and understand. Then when we go into 3D rotations, in 3D, rotations can also be defined as linear transformations, although parameterizing them is not as simple as in 2D. 3D rotation representations can be represented by a matrix equation as P dash is equal to RP, where, for example, we could say that R is equal to a 3 by 3 rotation matrix. So after rotation, the coordinates of the transformed point P dash relative to the orthogonal axis is determined via a matrix multiplication with the rotation matrix R. This is the rotation matrix R. So just like in 2D rotation, rotation matrices satisfy several properties. The composition of two rotation matrices R1 and R2 is also a rotation matrix. The composition of these two is also a rotation matrix. However, this composition is not equal. The determinant of the rotation matrix is 1 for all rotation matrices. And just like before, the transpose of a rotation matrix is also the inverse. And then vector norms are invariant. Again, these properties are for additional knowledge. Then let's come to scaling matrices. So what we basically do in scaling is we are given a scalar and axis aligned scaling in 2D about the origin can be represented as a linear transformation with matrix. So for example, scale Sx, Sy. If this, say this is the matrix that we are given, where Sx is the scaling about the x direction and Sy is the scaling about the y direction. If Sx equals Sy, then we say that this is a uniform scaling. Scaling is equal in both directions. So this definition can be generalized to an ND space using an ND scaling vector, which determines the scaling in each direction. So as you can see here, we have used several scaling factors. Here it is unscaled, k is 1. In the second case, kx is 2, ky is also 2. This is called uniform scaling, whereas these are non-uniform scaling because the scaling factor towards the x direction and the y direction are different to each other. Then when it comes to reflection matrix, here what we do is we kind of flip a figure. A figure could be reflected in a point or on a line or on a plane. A reflection maps every point of a figure to an image across the line of symmetry using the reflection matrix. So if you look at this, you have reflection about the y-axis over here, original object, and the reflection about the y-axis. And then you have the reflection about the x-axis. This is reflected about the x-axis and y-axis, both x and y. So if we take an example for the reflection matrix, so you have these points, you have a pentagon with these points A, B, C, D, E. And what we do is we write the ordered pairs as a matrix. So you have A coordinates, B coordinates, C, D, and E. And then when you want to reflect the pentagon across the y-axis, simply the matrix that you will use as the reflection matrix about the y-axis is this. So what you do is the matrix that you derived already will be multiplied by the reflection matrix. When you multiply, you get this answer. Then you mark the answers that you get in the coordinate space. So this is how the reflected pentagon would look like. When it comes to the shear matrix, this is an elementary matrix that represents the addition of a multiple of one row or column to another. Such a matrix can be derived by taking the identity matrix and replacing one of the zero elements with a non-zero value. So the name shear reflects the fact that the matrix represents a shear transformation. Geometrically, such a transformation takes pairs of points in a linear space that are purely separated along the axis and replaces those pairs by other pairs whose separation is no longer purely axial. So if you are using a shear which is parallel to the x-axis and your new coordinates are x dash y dash, this is equal to 1 lambda 0 1 xy. This is your original coordinates, these are your new coordinates. This is your shear matrix. X dash will be equal to x plus lambda y dash is equal to y. The y coordinate does not change. Why? Because this shear is parallel to the x-axis, just like what has happened in this case. The y coordinate does not change after the shear towards the x-axis. And then if we talk about the y-axis, how that works is your new coordinates are equal to 1 0 lambda 1. This is the shear matrix and you have x and y. So here x coordinate does not change, it is x. The y coordinate changes to y plus lambda y. Lambda x. This lambda is your shear element. Then when we look at the inverse of a matrix, if a matrix A has an inverse which is denoted by a to the power of -1, then their multiplication will be the identity matrix. So the inverse of a matrix, when you are given an n by n square matrix, B is said to be the inverse of A if AB equals to BA, and this is the identity matrix. Then we can say that B is the inverse of A. Just like this example. So we have A. We are supposed to show that B is the inverse of A. So what do? We take AB. We check this particular condition. If that condition is true, then we can say this is true. This is AB, this is BA, and finally it is equal to the identity matrix. Okay, now we come to orthogonal matrix. A matrix is said to be an orthogonal matrix if the product of a matrix and its transpose gives an identity value. If the product of a matrix and its transpose gives you an identity value, then we call that matrix is an orthogonal matrix. So that is to say that these two matrices are perpendicular or they form a right angle. So there are several properties of an orthogonal matrix, which I have added here for additional knowledge. So we can get an orthogonal matrix if the given matrix should be a square matrix. which is to say that we know that a square matrix has an equal number of rows and columns. A square matrix with real numbers or elements is said to be an orthogonal matrix if its transpose is equal to its inverse matrix. Or when the product of a square matrix and its transpose gives an identity matrix, then the square matrix is known as an orthogonal matrix. Okay. Suppose we have a square matrix A with real elements of n by n order, and AT is the transpose. Then according to this definition that we just gave, AT is equal to A minus 1. If this is satisfied, then we can say AAT is identity. This is the inverse, this is the transpose. Okay, so all identity matrices are orthogonal matrices. Product of two orthogonal matrices are also an orthogonal matrix. Transpose of an orthogonal matrix is also orthogonal. The determinant of an orthogonal matrix has a value of plus or minus 1. The matrix is orthogonal. If the matrix is orthogonal, then its transpose and inverse are equal. If it is orthogonal, then its transpose and inverse are equal. So these are, for additional reference, just some properties of orthogonal matrices.